This is AP Calculus, lesson 9-2. We're on standard S, approximating total change. Again, we are right in the middle of our unit. We're just talking about more formal Riemann sums today. All right, so we know the difference between infinite data and finite data. Infinite data is a line or an equation that they give us versus finite data, which is just a bunch of points or just from a table. So let's talk about what integration looks like visually. So if I'm taking infinite data, if I'm trying to integrate between A and B, this is going to be an infinitely many bars, so it's really just shaded in between A and B. And that is exactly equal to the integral between A and B of whatever function. My function, I'm calling it capital G of t. So capital G of t dt. All right, so what happens if I only have finite data? What does that graph look like? So I'll pause to make sure that we can see how I'm gonna write this. So I'm going to use this left point and then just draw a horizontal bar until I would hit the right point. And then I just make a bar that goes straight down. And I do the same thing with the rest of my points. So just from that left bar, go straight down. And you can see that what ends up happening is you get these bars. Okay, well, that bar should be like this. Yes. Although, do you need one today? I don't think a calculator is needed today. Today is all math in our head. So when I do this rate with finite data, this is going to be an approximate X estimate. So I'll write approximate here. Approximate. And therefore it's going to be, with this symbol, approximately the integral between A and B of gt dt. And this was an exact, so I can write exact over here as well. This is exact. So depending on how many points they give us in the interval that we're looking for, the more exact you would be. In fact, if you had an infinite number of points, then you'd have an infinite number of these bars, and you would basically be exact. In fact, that's where this exact is derived from. You take an infinite many bars like we have over here. Over here, we're going to have really big bars. And it's just rectangles. You can find the area of the rectangles. You do the height times the width, and then you can find the area of individual rectangles, and then sum those up. And that's what we're doing today. We're finding the area of each of the rectangles and summing them up. And that has a very special name, and it's called a Riemann sum. So these are called Riemann, with two N's, Riemann sums. So this is a picture of what a Riemann sum looks like. You will be able to do this without a picture, hopefully by the end of the homework tonight. All right, let's move to the next slide. All right, so I want to talk about a left Riemann sum. By the way, there are three types that you need to know for the AP test. There are actually a few other types that aren't on the AP test. So today we're learning about a left Riemann sum, a right Riemann sum, and is it called like a center? It's called, just a midpoint sum. All right, so let's start with a table. And I'm just gonna, that'll look more formal if I go like this. Copy this and paste, perfect. All right, so on our table, we want to say t in hours, and L of t, capital L of t, which is feet per hour for our units. And let's do 0, 1, 3, and 7. So let's paste some bars in here. And their corresponding values, 6, 8, 12, and 18. All right, so the question is, and I can maybe shrink this bar a little bit to have the question over here on the right-hand side. The question is, what is the approximate derivative between 0 and 7, those are the values that they gave us for t, of capital L of t dt. How do I approximate this thing? So maybe instead of saying this, I could say, what is this thing approximately equal to? Okay, so let's go ahead and make a picture. It'll make it easier for us. All right, so what times do we have? I'm just going to go by 2s, even though this isn't by 2, so I'm going to say this is 2, 4, 6, and 8. We end at 7, so I don't need to go beyond that. And I know that my maximum height is 18, so I'll just say 20 is about there. Half of that is about 10. Half of that in between here is 5, and in between here is 15, just to scale this accordingly. All right, so each of these pairs corresponds to a point, so let's graph the points. So 0, 6, I can do this in red to distinguish it. 0, 6 is right there. 1, 8 is right about there. 3, 12, so 3 is in between 2 and 4, so right here, and that goes up to 12. And 7, 18, so 7 is right here, and it goes all the way up to 18, so right about there. All right, we have our points. So the thing that makes a left Riemann sum is the fact that you use the points to make a bar stemming from the left, essentially. So if I was doing a right Riemann sum, I would go like this, because now it's on the right, but now I'm going to go for a left, so I'm going to draw it to the right, and I draw a bar. Bless you. Drawing a bar over here, and then making this into a bar, drawing a bar that goes out to the right like this, a little bit too far.
Wait, so you draw it out to the next?
You draw it out to the next one, yeah. So it should look like this. We can make these points a little bit bigger for our notes. All right, now we have to find the area of each of these rectangles. All right, so this was 1, this is 3, and this is 7. So what's the area of this rectangle? The first rectangle on the very far left. It is 6. Yeah, it's 1 by 6. What's this area's? What is this rectangle's area? It goes from 1 to 3, so the base is 2. 2 times 8, yep. 16, perfect. It goes from 3 to 7, so the base is 4. 4 times, yeah. So it's not 4 times 18, sorry. This height here is not 18. 18 is up here. So it's 4 times 12. 48. Perfect. So in our notes, this is what we want to write. We want to say that the integral between, I'm going to do this below here. So the integral between 0 and 7 of capital L of t dt is approximately equal to, and let's write out the numbers. It's the base times the height, 1 times 6, plus the base, which was 2, times the height, which was 8, plus the base, which was 4, times the height, which was 12, and we're still approximating, so I'll keep using squiggly equals to signs. So 6 plus 16 plus 48, that I think is 70. And if you want to make a note, all of these numbers, this is just the base times the height. All right, so we found an approximate area with the table data for a left Riemann sum. Okay, now the critical question here. Is this an over approximation or an under approximation? If we kind of look at the real curve, I can do the real curve in black here. If I looked at the real curve, which might have looked like this, is this an over approximation or is it an under approximation?
Over.
Okay, so either way, you're going to have to explain. So Carly, why'd you say under?
Yeah, I don't know.
Sophia, why'd you say over?
Because this is totally a guess.
And I was thinking like all the lines under, like there's like a line missing space.
Okay, so missing space. So missing space is really the key idea. So if I were just drawing the graph that looked like this, I should be shading everything under that bar. So everything would include this little area, and this little area, but we couldn't account for that. All of that little area we couldn't do. So we don't have enough of the area. This means that this is what? It is an under approximation. That is a very key thing for a left Riemann sum. So this approximation
So the left Riemann sums are always an under.
is less than the actual integral 0 to 7 LT dt. The reason for that, and we do need this too, is because LT is increasing on that interval. So we can say on the interval from, I don't know, where we're 0 to 7. But picture in your head, and you can maybe do a quick sketch out to the side, what would happen if I had a function that was decreasing? What if I had a function that looked like this? It was coming
Do you want us to draw?
down. Yeah, do a quick sketch. And I had something with a left Riemann sum.
You're panicking.
If I had a left Riemann sum, let me try to draw this line a little bit better. I can do this. If I had a left Riemann sum, then I'm still taking this point on the left, coming out to the right, taking this point on the left, coming out to the right. Come on, Mr. Sindel. Out to the right, and so forth. I'm taking this point, coming out to the right. Now if it's decreasing, it turns into what? And it's really just based off of the picture. Now it's an over approximation.
So it doesn't matter if it's left or right. It just matters if it's.
So there's a key thing. You have to know that it's left, and if it's increasing, then you need to know it's an over or it's an under approximation, and if it's decreasing and it's still a left Riemann sum, then it's an over approximation.
Then how do we know if it's a left or a right?
Good question. I'll talk about a right, and you'll compare it. All right, let's move on to a right Riemann sum.
So wait. So if it's increasing, then it's an under approximation.
Yes. So for the category of left, increasing means under, and decreasing means over.
And like that makes.
All right, let's do the right Riemann sum. Again, let's start with a table. And I can start a little bit farther over here. All right, so I'm going to go kind of the same thing. So this is going to be T in hours. And this is going to be capital L of T. And the units here are feet per hour. Feet per hour. And my values are going to be 0, 137. So it's the exact same table, but I'm going to change the values a little bit. 0, 1, 3, 7, and I'm going to go in reverse order now. I'm going to go 18, 12, 8, 6. Oh. All right, so okay, this is going to have to be a really quick sketch because otherwise we're going to run out of time.
Is this like almost the end of the box?
So we have right Riemann sum, and then we have midpoint sum. So let's graph these really quick. So we're going to go by twos. So we'll say that right here is 8, half of that is 4, half of that is 2, That's 6, and then it goes all the way up to 20 here. Half of that is 10. In between is 15. Half of 10 is 5. And quickly graph the points. 0, 18. 1, 12. So there's 1, 12. 3, 8. So 3, 8. And we need 7, 6. So 7 is right here. It comes up to 6. All right, what does a right Riemann sum look like? So instead of going to the right from each point, I go to the left. So this point, I go to the left. This point, I go to the left. This point, I go to the left. Maybe I should be using, I have technology. I can make it a little bit neater. This point goes to the left. So it looks like this. All right, now let's quickly find the areas.
So the first one is 1 by 15, 12.
1 by 12, so 12. Maybe we can stay with red. This next one is going to be
2 by 8.
2 by 8, 16, and 6 by 4?
Yeah.
Okay, 24. Perfect. That means that we can say our, we'll just kind of abbreviate this, so 0 to 7 of L of t dt now is approximately equal to 52 feet. All right, so, and then the critical question, this approximation, so this approximation is, okay, is it less than or greater than the actual value? Look at the points, make a line. Make your imaginary line that comes down through here.
So it's still an under.
This is an under approximation, and then you have to have the reason.
Because LT is increasing.
LT is not increasing.
It's decreasing. So that means when it's a right Riemann sum, an under approximation.
Yep,
Yes.
an approximation. And that's because L of t is decreasing on 0, 7. So on our side, we can say when you have a right, when it's decreasing, that's going to be under, and when it's increasing, it's going to be over. But this rule stems from just being able to draw a right and left Riemann sum kind of in your mind. All right.
And then for left, it's decreasing is over.
Yep.
Wait, do we have anything else on here?
Yes.
No, like, what's
You'll be fine. All right. Midpoint sum. Yeah, I guess it's midpoint Riemann sum, but I'm going to abbreviate midpoint sum. All right, so we have a lot more values here in order to get the data to come out nicely. All right, so again, t in hours. This is going to be L of t in feet per hour. All right, and we're going to do numbers 0, 1, 3, 4, 6, 7, 9. And the corresponding numbers, 5, 8, 10, 12, 13, 18, 20.
Mr. Sindel, will it always be where the numbers go in order? It won't ever be like 5, 8, 12, 9.
Sometimes they will do that, yes.
Okay. Does that affect it?
Yes, it does. All right, so we're going to go all the way out to, I'm just going to go out to 9.
You can make that on the entire page. And you have to go on this page.
Yeah, just make it
We'll make it
Oh, that gives me
10. That'll be better.
After all these, like, are this
So it's going to be
Yeah, the-
5.
I feel like
It's going to be 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Perfect. So what we also need on the side is going up to 20. Half of that is 10. In between is 15. And that's 5. All right. We have a pretty good idea of what's going to happen. Now we need to graph all these points. So 0, 5. 1, 8. 3, 10. 4, 12. 6, 13. 7, 18. And 9, 20. All right, so middle point. What happens with middle point? So if you can imagine each of these being connected by a line, so I'm just going to go ahead and do that. So I have to be careful here.
Wait, don't connect them by a line?
No, you do connect them with a line. I was going to say we have to do something else, but it'll work it this way. So
So do like a straight line.
yes. So middle point means I go kind of every other point, and I'm going to use that as my height. So what does that mean? So I'm going to say that my first, okay, well, this was a little bit off. But my first interval is going to be these 3 points, and then I'm going to do another 3 points. I'm going every other.
Why do you do that?
Because I want to have a midpoint in each of these intervals. So I need to have 3 dots instead of 2.
Oh.
Okay, so now what I'm going to say is, what is the base of this shape? Base here is 3. What is the height of this point right here?
12, 13, 12.
This is 1, comma 8.
8.
So the height is 8. The base is 3. This is 24. You take the height of the midpoint and then multiply it by the base. So the height for this point, this was 4, comma 12. So we want 1, 2, 3. So it's going to be 3 times 12. This is 36.
So it's the height of the midpoint.
Yep. And this is going to be 1, 2, 3 again. And then this point here, that's 7, 18. 3 by 18, that's 54. And we can make a note here off to the side. It's going to be base times midpoint height. And it is just going to have 3 points. If you have a ton of numbers, you're just going to go 3 points for every interval and then keep the same pattern. And if you take a note or take note to see what is happening, you're looking at this height, you're looking at this height, and you're looking at this height. The intervals in between. This is how to just go directly from the table. You're saying, okay, the distance between here and here was 3 with a height of 8. Distance between here and here was 3 with a height of 12. Distance between here and here was a distance of 3, height of 18. So you don't need to actually graph it. I just need you guys, you girls, to visualize what's happening. All right. Last thing in our notes, we're just going to write the approximate integral. So integral between 0 and 9 of LT, capital LT, dt is approximately equal to 3 times 8 plus 3 times 12 plus 3 times 18. And that's about, I think it's 114. And I guess we should have been doing units on all these. Feet, and I did do feet on all of them. Okay. This one should have been feet as well. All right, perfect. You have learned the 3 different types of Riemann sums.
How do you do the approximation? Is it over or under?
Ah, yeah, that's a good question. So what do you think this one is?
Over? Under. Just kidding.
It depends, right?
Yeah, I don't know.
So it really depends on if the area on the left versus the area on the right were the same. I don't think you're actually asked about the midpoint sum if it's an over or not, an under. You're only asked for a left and a right. So don't worry about midpoint. Just do left and right for over and under.
Okay, so no approximation necessary for midpoint.
You can do one, but yeah, not on the AP test. All right, that's it. Go ahead and do your summaries.